All right. Now we finished, pretty sure we finished this slide on power. Yeah, I'm sure we did. Yeah. So we're ready to start on page 67. This is chapter 3, energy, motion, position, and energy. But before we get going on that, I hope there'd be more people here. But I'll tell y'all it'll be recorded here. I don't know if anyone goes back to listen to it. But this week is a pretty normal, regular week as far as I can tell. Next week, however, there are going to be several somewhat minor and somewhat a little more major adjustments to my schedule anyway. It won't affect this class much, I don't think, at all. But let me start at the beginning. On Tuesday, I have an appointment with my hematologist, and he only sees patients on Tuesday mornings. I can't schedule them any other time. So it's 11 o'clock, and I hopefully will be through with him by 12, which means I hopefully will be back at campus by 12:45. But if he's bogged down or running late or something, and I'm not here at 12:15 on Tuesday, don't leave. I'll be here soon. I think I'll be here well before 1:15. 1:15. Second? Okay. If I'm not here by 5:45, you can leave. Okay. So, but I will. Knock on wood, I will be here much earlier than that. No. I will be having class. Whether you come or not is up to you. Okay. I never have bad moods, except when I'm going to meetings. No, I'm just kidding. Okay. All right. So that's Tuesday, which of course does mean my office hours will be cut to shreds. Because normally I have office hours from 10:45 to 1:15, since I won't be back here until probably close to, what did I say, 12:45. Well, I'll carry my lunch with me and eat on the way back. Okay. Don't worry, I'll take care of it all the time. Oh yeah. Oh no, eating's much more fun than that. Believe me. Okay. I'm just looking out. Oh, I see. Thank you so much. Okay. Yeah. I don't want to have to bring in a new teacher. Yeah. Okay. So that's Tuesday. Now, some of you may be involved in Thursdays, and again, it shouldn't affect this class any, but Thursdays is Honors and Awards Day. It starts, I think, at 9 in the morning on the Birmingham campus. Are any of y'all involved, or do you know? Yeah. It's not this Thursday, not day after tomorrow Thursday. It's next Thursday. You're okay. I thought some of you would probably be. So, what time have they told you when to be there? I got the invitation. I just didn't even look at it. Yeah. And I think it is like 9 something. It starts at. Well, I was told the student looked it up on this thing, looked up her email, and said it started at 9. But she's an ambassador. She said she had to be there an hour early, so that wiped out her 8 o'clock class. I'm sure they won't go on us there a little early because we have to dress for it. You know, y'all don't, but we do. And in our robes and that kind of stuff. Huh? Yeah. Okay, but no. It's 9 o'clock, so I'll be back here on this campus way before 11:15. I mean 1:15 without speed. Huh? Yeah. Most of them, yeah. So I mean, if you get an award, what you have to do? Just stand up, go, just stand up and sit down. That's it. Well, if you're getting an award, you walk forward and they give it to you, shake hands, take pictures, and you walk off. Yeah. Bring the whole family out there to take pictures. Yeah, if you're not there, they'll send it to you. Yeah, so. But they like having people there. If you're going to make me dress up in a coat, gown and hat and all that kind of stuff, you better know. I'm just kidding. Okay? All right. So that's Thursday of next week. Again, it shouldn't interfere with this class setting. So Tuesday and Thursday, I've got something that messes up my schedule, but it won't mess up as late as 1:15. Now, Friday, we don't have class, of course. This is next week, not this week. We don't have, well, wait, let me go over this week too. Because my Tuesday's appointment next week is messing, I'm going to miss all of my trig class. I met with the class this morning, and we decided at least the few that can come are going to come this Friday at 11 o'clock, and we're going to make up the class then. Okay, so that means normally on Fridays I'm on the Birmingham campus 7:45 to 1. This Friday I'll be on this campus probably all day, but I'll be out of the office from 11 to 12:15. So if you are looking for me Friday, I won't be on Birmingham. I'll be over here, and I'll be out of the office from 11 to 12:15. Okay, next Friday though, and this won't affect this class any either, but it does affect my office hours. Not this Friday, but next Friday, I have infusion all day. So I have to be at the office at the clinic at 8, and I have to get there before 8. So I won't be on Birmingham campus at all, and it goes usually until 4. So I will not be on campus at all on next Friday. Huh? Yeah, and they feed me crackers and cookies and things like that. Yeah, I have breakfast before I go, and then they usually. All right, I really appreciate it. And you who missed breakfast and skipped lunch, yeah, I can tell you what's on your mind. I mean, never mind. Okay. Okay, so that catches us up. I wonder where everybody else is. Whose stuff is that? He did? Oh, okay, Terry. Terry Wright. Okay. Okay. All right. Well, I'll catch him when he comes back then. I just hoped it wasn't someone from this morning's class. The stuff is still there. Okay. All right. So I guess we're ready to go. Any questions before we get started today? All right. Now, some were talking about it earlier. I did get all your labs and tests entered, those that have been turned in. And in doing so, I did notice a few things. I have one UNO paper in, research paper. And of course, after spring break, I was expecting to be flooded with them because y'all had worked on them during spring break to turn them in. Remember, this is your last month in this class, okay? What's that? Oh, okay. You did eat though, right? No. I want to make sure to watch out for you. Okay. All right. So only 1 out of 15 have come in, so please get those. Lab 1, I'm missing 1, 2, 3. Lab 2, I'm missing 1, 2, 3, and that just happens to be the same 3 people. Lab 3, I'm missing 1, 2, 3, 4, and 5. And 3 out of 5 are those same 3 people. Lab 4, missing 1, 2, 3, same 3. Okay. Not quite. I apologize. Not all these are always the same.
These experiments in the lab, right?
Yeah, that's it. Yeah. All right. Good deal. What's that? 5 labs so far. Yeah. All right. Good deal. Thanks. Okay. Okay.
I'm missing 3, but I ain't missing 1 and 2. You said all of them are the same?
No, yeah, starting with 3, there were a few more that were missing that weren't in the other. Okay. Yeah, that's the only one you're missing is number 3. Right. Okay, lab 4, I think I already said. Lab 5, Missing 1, 2, 2 out of lab 5. Okay?
Are those all the ones that I owed you?
I think so. Let me check and see. Yeah, you got the other 2 in. Okay. Test 1. I know it's in here somewhere. There it is. Test 1, I'm missing 1, 2. And test 2, I bet you is about the same. 1, 2. Yeah. So missing 2 people each. I'd love to be getting some of this stuff back to you, so I don't have to carry it around all the time. So please get your stuff in. Appreciate you getting those in today. All right, we just had Kemp come in.
Yes, sir.
And Mason come in. All right, good deal. Any other questions before we get going? I'm just harping on getting anything in that you're missing so far. I think y'all got everything in. Okay. If not, we're in the energy chapter. We talked about the time rate of change of energy, which is... Oh, yeah, that erased it. Etch-a-sketch, shook it up and it's all gone. Okay. Yeah. Huh? Oh, work, I see. No, work is the same as energy, equivalent to energy. The time rate of change of doing work or expending energy is power. You got it. So now we're moving into some types of energy. We'll look at the energy of motion, the energy of position, and just other energy in general. Okay? First, you mentioned work. Work and energy are related very, very closely. They have the same units. Energy is the ability to do work, okay? Whereas work is the process of changing an energy level, okay? For instance, if I'm doing work on this chair, I could be raising its energy level, okay? It has more energy here than it did on the floor. If you don't believe me, put your foot under here and I'll release it. Never mind. There's a lot more energy there, okay? So energy is the ability to do work, and work is the process of changing an energy level, okay? What we'll look at next is different forms of work and energy, specifically energy, okay? The relationship between the work and the energy associated with first position. Even though they mentioned motion first, we're going to do position first. The relationship between work and the energy associated with position, like I just illustrated with the chair. After that, we'll look at the relationship between work and the energy of motion. So there's the energy of position, energy of motion, the relationship between work and each of those. So that's what this next section, basically how we're going to break it down. So let's look first at potential energy, which is the energy associated with position, okay? There's several different types of potential energy we'll talk about. We're going to focus first on gravitational potential energy. In fact, today's lab is going to involve largely gravitational potential energy and energy of motion as well. So what we measure with gravitational potential energy is basically the change in height. Now they say H. I like to say delta H, the change in the height. In order to get the change, though, and to measure the height, we need to know what the reference height is. So if I were going to say, what is the energy level of this book when I hold it up here? If it has to do with height, where do I measure the height from? Yeah, from the starting point or the ending point. Because if I were to drop it from here, it would be the desktop. But if I go over here, it'd probably be the floor. If I hung it out the window, it would be the ground level. And if it was same height but over the sea, it would be a sea level. So really, your reference level is a pretty important thing to identify, okay? If you're dealing with something, you need to know the reference. What are you referencing it to? Now, if you do it properly, okay, and whatever properly means, most of the time your potential energy would be positive. But if you were referencing energy levels to the floor here, but then did all your measurements relative to the floor, but then hung it out the window, now the energy level down there is going to be negative compared to what it would be here. Positive up here, negative below the floor. So you could have either positive or negative potential energy, depending on that reference height. And one of the first things you'll do in the lab today is determine your reference height. Okay? Now, there are other types of potential energy. There's elastic, also called spring potential energy, as in compressing a spring. You're doing work to compress it. If you were to release that, then the spring's going to spring back, okay? Or if you extend the spring and release it, it's going to fly back in the opposite direction. That's elastic or spring potential energy. You also have electric potential energy, whereas you're moving a charge from one place to another place, setting up an increased electrical potential energy. What typical thing do we measure in electricity and electronics that is a measure of that potential energy? Voltage, you're absolutely right. Voltage isn't the same as potential energy, but very, very closely related. We'll do that in chapter 6, okay? Work can change potential energy. I've already illustrated that. How did I get the book from the desktop to up here? I did work on the book by lifting it, okay? If I released it, then the book will do work on whatever happens to be on the desk as it scatters it out there. So work can change potential energy, okay? Kinetic energy, which we haven't gotten to yet, can also change into potential energy, okay? Kinetic energy is the energy of motion. We're going to get to that a little bit later. But let's say that we're rolling. Remember in that second lab how we rolled the ball down the inclined plane? What if we did it the other way? We gave it energy on this end, kinetic energy, and then it rolled up the plane. So that kinetic energy could change into potential energy as you change the position. Because as it goes up, it slows and ultimately will stop and then come back down again. And actually today's lab will be talking about this interchange between kinetic and specifically gravitational potential energy. All right. The formula for gravitational potential energy. Here I wish they put GPE or PE sub G or something else so you know they're talking about gravitational potential energy. But here it is. MGH. M is what? Mass. G is acceleration due to gravity. And H is that change of height. I like to call that delta H. They call it H. Okay? If we were holding the book out of a 4-story building, like here, we only have at most a 3-story building here, but holding it out of a 4-story window, okay? If you're measuring from the floor here, then that would be the delta H. But if you're measuring from the ground, your delta H would be from here to there. But if you made this your reference position, but then dropped it to the ground, now you have a negative H here because this final position is a lower elevation than your reference position, so that would be a minus MGA. I usually don't. I usually want to choose my reference level, or that's on the previous slide, the reference position to be as low as you can go in the given problem. Now, if I'm just going to stay in the room here, there's no reason to make the ground the reference level. But you could. But if I'm staying in the room here, the floor would be as low as I can go. If I'm hanging out the window, there's no reason to make sea level the reference position because I'm never going to get down to the sea. You know? But if you're measuring, say, the potential energy of water somewhere up at Lewis Smith Dam and measuring that compared to what it will be when it ultimately flows into the Gulf of Mexico, yeah, then you might want to choose sea level. So it depends on your problem. To me, this is sort of ridiculous to do it this way, but it could happen, okay? If you chose your reference position here your height is 0, and because h is 0, your potential energy is 0. If you increase the height from there, you have a positive potential energy. If you let the height go below that, you have a negative potential energy. Now, is that the smart way to do a problem? Probably not, but you could do it that way. Okay. Man, is that all she wrote? Not really. Let's do example 3.5. So let's go back here and do example 3.5. What is the potential energy of a 2.14 kilogram book? Whoa, let me get my pen adjusted. Okay, 2.14 kilogram. What's that a measure of? Mass, okay. That is on a bookshelf 1 meter above the floor. What would that be in our current parlance? That's your height, exactly. Or delta H if you wanted to call it that. And it said, what is the potential energy? What is potential energy? And we're talking about gravitational potential energy. That's what I like to call it. You could call it PE sub G or something like that, but potential energy alone, to me, needs a little something else there. What is GPE? What's the formula for it? Gravitational potential energy. Is weight times height? Actually, that's very good, but weight is mass times acceleration due to gravity times height. That's it, mgh. Weight times height. Now, by the way, think back on work. What was work? Force times the displacement. Force is your weight, displacement is your change of height. It's the same formula, isn't it? Okay? mgh. So what is your gravitational potential energy there? And by the way, notice it said on a bookshelf 1 meter above the floor. So that makes it a plus 1 meter. Okay. So what's your M? 2.14 kilograms. What's your G? 9.8 meters per second squared. And what's your height? 1.0 meters. So it's not going, the height doesn't contribute too much to the numerical answer, but it does contribute to the units, which does affect the answer. So what would this be? If someone got a calculator? 2.14 times 9.8. Say again? 2.14 times 9.8. Say again? Yeah, times 9.8. 20.97. What units? Kilogram. Meter squared per second squared. You know a simpler unit for that? So Newton meter, which would be a what do women love? Joule, very good. Okay, he knows his women. Oh, never mind. Okay. So that would be what? We don't have 4 digits of precision here. In fact, it looks like we only have 2, so what would you round that to? 21 joules, approximately. Okay, and that's exactly what they got. Good for them. See how that works? Okay. Everybody got that? Clear that if everybody's got it. Then let's do 3.6. How much work can a 5 kilogram mass, oops, they told us what it was. That's your mass. do if it is 5 meters above the ground? That would be your what? Height. Okay. Fairly similar question, just different numbers. How much work can it do? In other words, how much potential energy did it gain? That's what work is, change of potential energy. So the work is, same formula by the way. What is it? Say again? mgh, same as we used before. What's your mass? 5.00 kilograms. What's your G? 9.8 meters per second squared. And your height? 5.00 meters, which is a good ways up there, by the way. And 5 kilograms is a fairly decent mass. So what does that give you? 9.8 times 25. 245 what? Joules. Excellent. Okay, 245 joules. Now, if they decide only to round that to 2 digits, they may give the answer as 250 joules. What do they do? Yes, they do. Which to me is a little...
Why you call that 2 digits?
Second?
Why you call 250 2 digits?
Because, you see, this has 3 digits, but that only has 2, that has 3. So you go with the fewest number of digits. This has 3 digits, so you round. You look at the second digit, look to the right, it's 5 or greater, so they rounded it. Yeah, well, to the nearest 2 significant digits, and that would be 2, 5, and 0 not being significant. I think that's a little stretching it, okay? But that's what they do.
245 or 250 could be the answer.
Yeah, that's close enough for government work, okay? So, either answer I'll give you full credit for. Okay. Now they have a little blurb here on work and power, concepts applied here. Power is the rate of expending energy or of doing work. That's what we talked about before. And guess what they do? They talk about walking and running the stairs, exactly what we did in the last lab. So you can read through that and deal with it as you like. Okay? That's all they write on potential energy. Let's move on to kinetic energy. What does the word kinetic imply? Second? Motion, exactly. You have 2 types of friction. Static friction and kinetic friction. Static friction is the friction that keeps me from falling down because I slide on the greasy floor. Okay? Static friction. It's not greasy, so I can stand here. I can even do this and not slip around. Okay? Kinetic friction, though, is the friction that if I'm going along and then try to stop, the friction that stops me. So kinetic means motion. So this is the energy of motion. Energy associated with motion. It results either from work or change of potential energy. Okay? Baseball season's in play now, all right? And that pitcher is throwing that ball hopefully across the plate. The reason the ball has kinetic energy is he does work on it. He moves the ball. He does work on it. So much, whatever its mass is, times the acceleration that he gives it, times that would be the force he would apply over what distance is he applying that force. That would be the work he's done. Or it could be a change of potential energy. If someone dropped a ball from the top of a stadium, they didn't really do any work on it, but it's changing its potential energy as it falls. It's gaining kinetic energy, going much faster right before it hits than it did when it left its hand. Now, The formula for kinetic energy is this one. Kinetic energy, 1/2 mv squared. Now, are those the right units for energy? What are the units for energy? Any energy. Okay, MGH. Let's talk about potential energy. MGH. What are the units for that? We just did them. Mass is measured in second kilograms. G is measured in G meters per second squared. Now that's an acceleration, meters per second squared. And height is measured in meters. So kilogram meter squared per second squared, that's also a, no, Newton is kilogram meter per second squared. Huh? Joule, this is a joule. Okay? And let's see what kinetic energy is. What's mass measured in? Or kilograms. SI is kilogram. Velocity? Meter per second. But you square that, so it's meter squared per second squared. Sure enough, it's the same unit. It's also a joule. Kilogram meter squared per second squared is a joule. And that's what you measure energy or work in. Okay? Now, the key here is that kinetic energy varies not directly with speed, but with the speed squared. Okay? That means if you double your speed, your kinetic energy goes up by 4 times. Triple the speed, it goes up by 9 times. So it's the square of the increase in your speed. That's why, folks, we don't tailgate, right? Right. Because the faster you're going, the longer, number one, the longer your reaction time is going to be. Because, well, your reaction time may not be any longer, but you're going to go a lot longer distance. But even with 0 reaction time, if you could react immediately, then you're going to have to add enough energy to the system or take energy away from the system to stop. You're going to have to, if you're twice as fast, you're going to have to allow 4 times as far to stop. Okay? That's what it comes down to. Okay? That's what comes with the squaring the speed. Okay. Maybe we beat that to death. Let's move on. Okay. Before we get to energy flow, let's back off and do another couple of problems here. 3.7 and 3.8. Here we have a 7.00 kilogram. What's that a measure of? That's your mass. It's a bowling ball. Moving in a bowling lane with a velocity, so they've already given the velocity is 5.00 meters per second. Okay? What is the kinetic energy of that ball? What would that be? What's the formula for kinetic energy? 1/2 mv squared. So this would be 1/2. What was your mass? 7.00 kilograms times what's your velocity squared? 5.00 meters per second, but you're going to square that. Okay? That would be, I'm going to write this as 0.5. That's the same as 1/2. Times 7.00 kilograms. And then what is 5 meter per second squared? 25, I'll put it 25.0. You also square the units. meters squared per second squared. Not just the number you square the units as well. Okay? Because that's all in the parentheses. Say this again now. Oh, okay, yeah, when you multiply that, 3.5 kilograms, if you multiply those first, and I think I would go on and make it 3.50, because this 1/2 is exactly 0.500. You can put as many zeros as you want to after it, because it's exact, okay? So that's 3.50 kilograms times 25.0 meters per second squared. So if you got a calculator, 87.5? 87.5, what units? Joules, because that's meter squared per second squared. That would be kilogram meter squared per second squared, joules. All right. And they came out with 87.5 as well. Good for them. What's that? Oh, you were thinking of that all night, weren't you? Oh, you were. Right. You could have used it. Yeah, absolutely. All right. Oh, yeah, you got enough kinetic energy, though. You should get some points for that, right? All right. If everybody's got that one, let's move on to the 3.8, which is a 100-kilogram football player. What's that a measure of? That's his mass. Okay. I'm sorry? That would be about 214 pounds. So, reasonably decent sized linebacker or somebody like that. Okay. What's that? Is how much? 107 or 70? Now say that again. Okay. It's not really a fair conversion, but they say that. Wait, I may have said it wrong. Backward. No, I said it right. A kilogram is 2. I know it's not in your book, but it's about 2. I'd say 1.4, but maybe 2.4, because that's not a fair conversion at all, because they measure different things. No, 2.2. Sorry about that. They do put this in your book. I'm surprised. No, you don't, but I do. It's 2.2 kilograms. So that'd be about 220 pound football player. For some reason I had 2.14, but it's 2.2. Okay. Football player moving with the velocity. His velocity is 6 meters per second. Okay. Tackles a stationary quarterback. Crunch. How much work was done on the quarterback? Okay. The football player who tackled him started with so much kinetic energy and then used all that to do work on the quarterback. So how much work was being done if he used all that energy? What was his change of kinetic energy? From this to 0, so that would be all this. So how much kinetic energy did he have? KE was 1/2 mv squared. So that would be 1/2 times the mass, 100.0 kilograms, 6.0 meters per second squared. 1/2 of 100 is 50, so that would be 50.0 kilogram times 36.0 meters squared per second squared. And actually there, I think we just say 36. You don't have enough to say 0.0. Multiplying those out, what do you get? 1,800 joules. Now, if you wanted to do a bigger unit with a smaller number, what would that be? Say again? 1.8 what? Kilojoules, exactly. 1.8 kilojoules. Kilo means 1,000. It's 1,800 joules. That would be 1.8 kilojoules. Exactly. Okay. Now that reminds me, I went to a very small high school in Georgia, so we were small enough just about anyone could go out for football. And I think it was either my freshman or sophomore year. Seems like it may have been spring practice, but I don't know for sure. I was second string defense playing against the first string offense. And Bill Boyce lived right up the road from us. His family had a dairy. So whereas most people drink water, he drank milk. I mean, he was one big solid guy. He was at least 190 pounds then in high school. I'm guessing I was about 170 then. It's been a long time, so I don't remember for sure. But I remember I was playing defensive end, and he was a fullback, and the play was coming my way, and I knew it because the pulling guard came out, and surprisingly, I escaped the pulling guard. You know, he was going low, and I sort of swiveled some and got him to go past me just in time to look up, standing still, Bill Boyce coming full speed right at me. All I had time for was to get my arms out and try to grab him, and all I felt were knees just pounding me to death as he dragged me down the field. So I felt like this quarterback going the opposite direction, of course, but I did get him tackled, but it wasn't a very pretty one, and it certainly wasn't a painless one either. Okay, but Bo Jackson and who? Okay, I didn't remember the second guy. Yeah.
They hyped him up in college like he was some superhero. And Bo Jackson come running around there and ran him over.
Yeah.
And kept going.
Yeah.
You never heard much out of Bosworth.
Bosworth. Okay, I remember him now. Okay, I wasn't hearing well. Yeah. Yeah. Of course, what is that emblem that you have? Oh yeah, Auburn University. Okay. You would remember. I do know, probably not worth it now to tell a Bo Jackson story, but we have a good friend of ours. He's a carpenter, an excellent carpenter, and he's done a lot of work for us at our house and various places. And we were putting an addition on the lake cabin, and he was sort of the general contractor doing it. And I went up, it was probably spring break week or something like that, to help when they were putting the floors down. So I was helping as much as I could. And one evening after we had finished, he was talking about, because I knew he ran, races in town, like 5Ks, these various things. So I figured he was a pretty good athlete. I think he went to Homewood High School. So I said, well, yeah, you probably played sports in school. And he said, yeah. He said, I was a good runner and good, but I wasn't the fastest at anything. And he said, I was running track, and I could sprint, but not as good as some of them. I could do distances, but not as good as those. And he said, I was just sort of in between. And the coach said, because he was a good athlete, he said, you might try the decathlon, which is 10 different events, variety of events. I mean, all over the place. A sprint is involved, but also a mile run is involved, or something. I mean, and lots of things in between. What's that? Yeah, shot put, lots of things. And he said his sophomore year, he came in third in the state. And no, not yet. He said, and the two that beat him were seniors. He said, I own this for the next 2 years. This is going to be mine. And they had some summer program that helped track and field athletes, one of the schools, colleges or something did. So he was participating in it. He said there was this kid from McAdory who was there, and he was also participating in decathlon, but he could not pole vault at all. Okay, and that's one of the events. And so he got with him, and they got to be sort of friends. And so John gave him just a few pointers on what he could do to improve that. And being a quick study, he picked it up really well, and soon could do pole vaulting. It still wasn't his strongest thing, obviously, but he could do it. He said Bo Jackson beat him for the next 2 years, and probably the year, he was graduated, and Bo was there around for another year or two. The kid was Bo Jackson, and he owned that event.
Kansas City in baseball, and threw a guy out from the back wall.
Yeah, I can believe
it. The guy running home was wondering where did this ball come from. Yeah. So it was like, usually they'll throw it to somebody in the infield, and then they'll
relay,
So he threw it all the way home.
Yeah. So anyway, that's my only Bo Jackson story I know. But except he was a phenomenal athlete. What's that? Yeah. Okay, so that was 3.8. Any questions on kinetic energy? Let's move on to, I guess, did we do this? I know I talked about it, but that's not what I want. Yeah. We talked about it here, but I didn't show this slide. I don't recall showing it. If you double the speed, kinetic energy goes up by 4 times, not twice. I recognize this gal from somewhere. Who is that? Okay. And remind me before you leave that I do have some papers for you. Okay. All right. And I also need to talk to you about something else too. Okay. But that finishes. Let's see. That was just the last slide on kinetic energy. Now let's move to energy flow. That title there is a little bizarre, isn't it? Energy. Has anyone ever seen any energy? I felt energy when Bill Boyce was running over me, but I didn't see it, okay? So why do we say that energy flows? We use that term a lot, but in reality, it has to have material substance to flow. One reason for that, and this is just a minor little thing, and by the way, energy, if you're having trouble keeping straight what is energy, what is work, what is power, what is force, don't feel like the Lone Ranger, because lots of people, scientists, had trouble and arguments over what was what for many years. Way back when they first came up with it, they thought energy, in fact, good old Aristotle, we mentioned him, like 400 BC, way back there, he said there were only 4 elements. I think I've mentioned them before, haven't I? Earth, wind, fire, and water. Okay? 3 of those made a signature, remember? Okay, but never mind. You would remember, y'all wouldn't. Okay. But look at what was in there. Fire. Fire is not an element, but for the longest time it was believed to be an element. Even after, they say, 1600s or so, when the Lavoisier, a Frenchman, put together the first list of pretty close to our current table of elements, guess what he had in there? Caloric, which was, he didn't know what it was, but it was that same concept of energy. He was thinking heat energy. For the longest time, they counted energy some ethereal substance. So they talked about energy floating. And in reality, it sort of acts like it flows, but it really doesn't. It's just there. So energy can do work as work against inertia. What would we mean by that? What is an example of work against inertia? Say again? Someone say something?
Like you're pushing something.
Yes, like you're trying to push a car. You know, your car's stalled and stuff like that, trying to jump start it, right? Pushing the car off. You're working against inertia. Pretty tough work there, okay? Or, how about the catcher for some of these fastball pitchers? They're working against the inertia of the ball coming in, trying to get it to stop, okay? Sore hands, okay? So that would be work against inertia. Work against gravity, lifting the book, or lifting anything against gravity. Work against friction, okay? Pushing against the desk. The desk wasn't really that heavy. It's the friction of the feet to the floor, you know, working against friction. Working against shape. What would that be? Okay, squeezing a ball, that would certainly work. Have you ever seen a time-elapse photograph of just about anything? I've seen it of a tennis racket hitting a tennis ball. That makes the ball almost go flat, whereas the back of the racket is actually bulging in the opposite direction. If you do the same thing, believe it or not, with a baseball, that baseball kind of wraps around the bat and pops right back. That's elastic. You know, it comes back to its original shape. That's work against shape. Have y'all ever played volleyball? Well, how would you describe a volleyball to me? Hard, soft? Okay. Softer than a baseball or a golf ball. Oh, by the way, golf balls too. See a picture of a club hitting a golf ball? It almost goes flat. You know, and the club, if you look at it, the shaft bends back like this. You know, that's what gives, and the shafts they have these days get it further, okay? That's working against shape. But a volleyball is not a super soft ball. I mean, it's pretty hard. I mean, yeah, it's got air in it, so it will give some, okay? But I remember when I was in college, I liked to play intramurals. I needed to do something to keep from putting on weight too much, but also I just enjoyed getting out and doing something rather than studying all the time. Of course, that's what I was doing. Okay. But anyway, we had, when I was in Nebraska, a group of us from ministry we were in decided to have a co-ed volleyball, join the co-ed volleyball league. We thought that would be fun. And it was. And we went to play this one team, and we were watching, how they stand around, hitting the ball up. And there was this gal on this team that had to be 6'1" or 6'2". And you could tell she had played some serious volleyball. And she had a little setter that could just set it perfectly for her. We knew we were in deep trouble, okay? Because they knew what they were doing. Now, we had a couple of tall gals on our team too, but these were semi-pros, they really looked like it. And, in volleyball, you rotate around, and when it got time, when I was on one side of the net and she was on the other side, you knew it was coming, I can't remember who served, maybe we served, and it went over there, and someone got it up right to the setter, and she set it up right across the net from me to this spiker, and they have a name for it, I don't remember what they call it, set it up perfectly for her. I knew it was coming, so I went up as high as I could go, my hands together, give it as much surface area to do all I could to see if I could block that thing, because I knew it was going to come flying over there. Well, it came down at an angle so that it hit me square in the face. And literally, I felt that ball touch both ears at the same time. And that was not a soft volleyball at all. All I could see was Wilson, but it was awful, okay? And the ball fell on my side of the net. I mean, at least it could have bounced across the net, it just dribbled on down my face, or maybe my face dribbled down, I don't remember, but anyway, that was work against shape. Not selective work, but yeah, say again? Yeah, I did. Too late. Okay? Or work against any combination of these. Now, they're going to give us a lot better examples than I did. Oh, well, here's the guy pushing off the car. Fortunately, it's a Volkswagen, but he's working against inertia. Okay? His force is in this direction. Hopefully, the distance will be in that direction. If it does move it, he's doing work. Of course, if they left the brakes on and he can't move it, how much work did he do? Zero, because you have to have the displacement to have work. Even though he pushed just as hard, he did no work. Work against gravity, lifting the box, or lowering the box, then you're doing negative work against gravity. It's actually helping you. Work against friction, gal pushing the filing cabinet across the floor, just like me pushing the desk, that would work. Her force is in the direction, she's pushing there. Friction is resisting the force, and by the way, friction always is in the direction opposite to the applied force. Whether it's sliding friction or static friction, kinetic friction or static friction is always against the force. Their work against shape was, of course, the shape of a spring when you stretch a spring or compress a spring. They're showing the compression of the spring. You compress it a certain distance. The shape of the spring went from here to here, so therefore you did work against it, and it's pushing back on you all the time. Okay? And then any variety of those. All right, so let's move on from energy flow to energy forms. Now, their work and energy section in the book went over the things we just said. So we'll move on to energy forms. If we didn't have enough forms of energy, here's a few more. Mechanical energy. And get this, because you'll need this for lab today too. And it actually, I want to make sure that it does show up in your book. In the earlier editions, it did specifically. In this one, it just it's not as clear as it is on the slide. But in your text, it says, the form of mechanical energy is usually associated with the kinetic energy of everyday sized objects and the potential energy that results from gravity, okay, or from something else. So here is the formula for it. Mechanical energy is kinetic energy plus potential energy. The sum of those two energies. Kinetic being the energy of motion, potential the energy of position. Mechanical energy is the combination, the sum of those two. You'll need that for lab today. Other forms of energy. Electrical energy. We already talked about it. If you got two charges, in electricity you have two charges, positive charge and negative charge. If you're pushing, okay, you name which one you want this to be. Positive, negative, what? Positive. What do you want this one to be? Positive or negative? Negative. Okay? Are you having to push it to get these two to come together? No, they're going to come together no matter what. To keep them apart, you're having to do work because they're attracting to each other. That's a rule of electricity. The like charges attract each other, but if this was positive and that was positive, you're really going to have to do the work to get them to move because they don't want to get closer together. Okay? So that is electrical energy. The movement of charges, which movement of charges currents, that all deals with electrical energy. We'll get to that in chapter 6. Chemical energy. Now we're barely going to hit this. This will be chapter 8 a little bit, but we really won't get there. That's the energy involved with chemical reactions. There are some chemical reactions they call endothermic, meaning you have to add heat to make them happen. Okay? There are other chemical reactions that are called exothermic. Those are reactions that when they happen, they give off heat. Can you think of an exothermic reaction? What? Burning of fuel in a car. Exactly. Burning of paper, burning of wood. You know, oxidation is just about always an exothermic reaction. You're changing the chemical energy. See, these little green leaves on the trees out here are absorbing the energy from the sun, the radiant energy from the sun, and what they're doing when they're doing that, what are they doing with it? They're taking water from the soil and carbon dioxide from the air, and they're changing the chemical structure and endothermic reaction. It requires energy for that to happen and making these complex carbohydrates. I think I wrote the equation on the board some earlier class, didn't I? Okay? That's an endothermic reaction. And you're making sugars, simple sugars. Now we eat some of those sugars, like I ate an apple today. That was stored sugar from an apple tree. Okay? But others of those sugars are being formed into starches, and a very complex starch is called cellulose, wood fiber. Now sometimes that undergoes other long-term chemical reactions that change it to coal or petroleum. And we take that and get our gas or other things from that. Those are all chemical reactions. Many of them endothermic until we take that wood or take the coal or take the petroleum and then oxidize it, and then it becomes exothermic. We're reversing that, and what do you have left over? You have water vapor and carbon dioxide. So you see you've gone one way and then another chemical energy. Some is storing, some is taking away, some is increasing chemical energy, some is decreasing and making more heat energy. Radiant energy. The sunlight hitting the leaves, that's radiant energy coming in. Electromagnetic energy, that could also be between the charges. Visible light is a very small part of the full spectrum of light, of radiant energy coming from the sun. Thank you, atmosphere, that you block off most of that electromagnetic energy. The gamma rays will kill you. The X-rays will damage you and ultimately could kill you. There's all sorts of high energy. The ultraviolet rays will damage you. In fact, they do damage you. What are some evidence that ultraviolet rays damage you? Skin cancer, absolutely. Now, some of you have a lot more melatonin in your skin and are more protected from that than others of us, okay? The fairer the skin, the less you have, and the more likely you are to get skin cancers. I've had one removed. This is precancerous here. I have to put stuff on it every day to try to prevent that from proceeding to form a real skin cancer. Not just that. Wrinkles in your skin. The older you get, the more wrinkly you get. It's not that funny, okay? Because of that very thing, okay? I've had a cataract removed. Cataracts are caused by ultraviolet radiation being in the sun. Now, for some reason, my right eye had it before my left eye. I've got a small one in my left eye, but if you live long enough, you're going to have cataract because you're exposed to ultraviolet radiation. We see it all the time, okay? You all are young, you don't realize it, but it's going to happen. But even just a sunburn is caused from the ultraviolet radiation burning your skin. It's not a healthy thing, okay? And that's what a suntan is. Your body is trying its best to get you darker so you can repel that, and that's why you get a suntan. Not necessarily a healthy thing. It's better to have it than burn, but So visible light is just a small part of that full spectrum. Then we have nuclear energy. Where did the electromagnetic radiation from the sun come from? Nuclear energy that's happening on the sun. Continuously, nuclear reaction. I mean huge nuclear reactions happening on the sun continuously. Okay? We also have nuclear energy we do here on the planet with nuclear power plants, either in ships or submarines, or making electricity. And unfortunately, we've done a couple of bombs ourselves, and others have experimented with them, tested them, but unfortunately, no one else has dropped any. They won't. So that's energy involved with the nucleus and nuclear reactions, and you talk about huge amounts of energy being released very, very quickly. Okay. All different energy forms. They have several pretty good pictures in the book. One is mechanical energy of the boat, driving you through the water, overcoming frictional energy. Actually, water does have friction, okay? And the propeller pushing against the water is what pushes the boat forward. The wood stack there, we've already described that. Radiant energy from the sun that came from nuclear energy on the sun, converting into tree leaves to complex carbohydrates like cellulose, and then we burn that and change it back to carbon dioxide and water again. Here's a guy standing on a coal heap. Have y'all ever been to Birmingport? I've driven by there several times. I've never stopped. Unbelievable piles and mountains of coal they have there for the barges to pick up and the rail lines. Pretty impressive. But here, that is coal, which is stored chemical energy from tree leaves of a long time ago that's been converted. Next page, page 72, you see solar cells, a solar farm, solar cell array converting radiant energy from the sun directly into electrical energy so we can use that. Okay. Now we're ready for energy conversion. I kind of don't like the any here. I would rather say most forms of energy can be converted into another form. Because there always gets down to be that wasted energy of heat, friction. For instance, now I know that some cars use regenerative braking to convert back to electrical energy, which is a very good thing to do. But the standard old brakes, where's that energy going? Heat. You felt of a brake pad shortly after it's come into the shop? It's hot. Okay, isn't it? Don't they warn you against touching it? Because if it's been driven much, there's enormous amounts of heat. That low-level heat is very hard to convert back into other forms. Okay? That's why I don't really like to say any form of energy can be converted, but most forms can be converted into other forms. Energy flows, and here again, they use that term flow, from one form to another in natural processes. Okay? Like the radiant energy hitting the leaves, the natural process of photosynthesis, light synthesizing compounds, changing it to stored chemical energy, that's a natural process. Okay? Once it's in the ground and gets buried under pressure, that changing to coal, that's a natural process. Changing to petroleum, that's a natural process. Okay? All these energy forms changing from one to another, back and forth, that's pretty much natural process. Now, we have learned to manipulate those and make them happen to our advantage. Okay? An example of a sort of a natural process is a pendulum. Well, that's not a pendulum. This is Charles bowling last night. Okay? What he's doing here, what's the first form of energy conversion he's doing? Yes, against the ball, against gravity, he's lifting that ball, increasing what kind of energy? Gravitation potential energy, exactly, the energy of position. He raises it up here, right? That's where most of the work is, right? But then, not just that, he increases the velocity of the ball by swinging his arm around, giving it greater kinetic energy. Because up here it has gravitation potential energy. His muscles are converting some of those sugars and other things. And now Terry's here. We saw your stuff, but didn't see you. Okay. All right. And he's also, his muscles are converting stored chemical energy into energy of motion. So between the change of height and the energy that his muscle is pushing on the ball, it gives it kinetic energy. That kinetic energy is then used to do work on the pins of course, hitting all those pins, all 10 of them, knocking them all down every time, right? Good man. Never in the gutter, okay? That's doing work on the pins. So you change from stored chemical energy, potential energy, gravitational potential energy, to kinetic energy to work, okay? And gave the pins kinetic energy. They were stationary, now they're moving, the ball's slowing down, okay? Not a pendulum, but another example of energy conversion. Here's the pendulum, okay? Now the pendulum can be either on a fixed rod that does like this, or it could be on a cord. The one we're going to do in lab is going to be on a cord, okay? Now, what you do, you start at a position down here. As low as you can go, what would you call this position here? Your reference position, exactly. That's your zero reference level, right there. That's going to be your zero potential energy when the pendulum is down there. Okay? Usually you have a mass on the end of this. The string or the rod is usually fairly light compared to the mass here. And that's what gets moved. When it's moved up here, what are you doing? Increasing its potential energy. And when you release it from here, what's its kinetic energy? Release from rest. Kinetic energy, energy of motion. If you release it from rest, what was this energy right up here at the top? Zero, because it has zero velocity. Exactly. So it's all potential energy here, all the energy that's in this. Now what's the sum of the potential and kinetic energy? Sum of, say again? Someone I thought said it. Mechanical energy, okay? That's the sum of kinetic and potential, okay? So the sum of this, whatever it is, all of the energy is potential here, no kinetic. All of the mechanical energy is potential energy, no kinetic, okay? When it starts to fall, when it gets to a zero reference level though, what's this here? Any potential? No, you set that as your zero level. It can't go any lower than that. So it doesn't have any more potential energy here. So all of its mechanical energy is now kinetic energy here. Okay? Somewhere in between there, when it was half the height there, half of this was kinetic energy and half was potential energy. What happens when it gets here? Does it stop? Not unless you stop it and then you do work on the system. It continues, and what happens as it goes here? It's changing again. Now the kinetic energy that was here is changing to potential. How high can it go over here? Only as high as it was to begin with. If it had no kinetic here, it can't have any more mechanical energy here than it does there. When it reaches all that as potential, it can't have any more kinetic. So it only comes to that same level and goes back and forth. Now, if you threw the ball from here, now you're giving it kinetic energy. You gave it a velocity. So now it can go higher over here. That's why pushing someone in a swing, they can go higher up there than they were back here because you gave them kinetic energy. You didn't start with zero kinetic energy. You gave them kinetic energy with the push. Okay? But a pendulum that you don't throw it, you just release it from rest, zero kinetic energy, you'll have zero kinetic energy here too, because all of the potential is going back. Okay. Here is the equation. And what could you put in front of here? What is this energy? Mechanical energy of the pendulum is fixed, it's constant throughout, it doesn't change. It's the sum of the kinetic and potential, which are always changing. Decreasing, increasing, increasing, decreasing, okay? Throughout the process. Does that make sense? Okay. Before we move to energy conservation, let's do examples 3.9 and 3.10. Okay. 3.9. A 1 kilogram book, you know what my question is going to be. Mass, very good. Falls from a height of 1.0 meters. Looks like our calculations are going to be pretty simple on this one. What is this velocity just as it hits the floor? What is V final just before it hits the floor? Okay, let's go back and check our problem. A 1 kilogram book falls from a height. That indicates it wasn't pushed from a height. It didn't jump from a height. It fell from a height. So what could you say to begin with? What's that? At rest. So its initial velocity was 0, meaning it's what kind of energy is associated with velocity? No. Potential is identified with position. Kinetic. So your initial kinetic energy was 0 because it's 1/2 mv squared. And if your v is 0, your kinetic energy is 0. But what was your initial gravitational potential energy? Remember that one? Okay, mgh. And that's 1.0 kilograms times g is 9.8 what? Meters per second squared. That's an acceleration times h, 1.0 meters. Okay, now those ones aren't contributing much to the problem, but the units certainly are. So your initial gravitational potential energy was 9.8 joules. Excellent. Okay. Now, right before it hits the floor, okay, that 1 meter was above the floor, didn't it say? From a height of 1 meter, we'll assume that's above the floor. So if the floor is your 0 reference level, that's where you measure your 1 meter from, what's your gravitational potential energy right before it hits the floor? Right before it hits the floor. Right before it hits the floor. 0. Okay, I thought someone would pick up on the hint. Okay, your H final is going to be 0, or awfully close to 0, right? So what is your GPE final? It would be 0. Now, let's back up a minute. If your initial kinetic energy was 0, your initial gravitational potential energy was 9.8 joules, what was your initial mechanical energy? 9.8 joules. You got it, because your mechanical energy is the sum of kinetic and potential. Okay? So at the bottom, your GPE is 0. What do you reckon your mechanical energy at the bottom is? It's 9.8, because guess what? Mechanical energy is conserved. That's what we're going to talk about next, but it is conserved. We mentioned that on the last slide, our race to get here. Okay? So if the GPE final is 0, but mechanical energy final is 9.8, what does that make your kinetic energy final? (9.8). Okay, because kinetic plus potential is mechanical. Okay? Well, now we can figure out what the V final is. Because how is V final related to KE final? What's the formula for kinetic energy? 1/2 mv final squared. You've got it. So what I like to do is write that 9.8 not as 9.8 joules, but as 9.8. What is a joule in fundamental units? Kilogram meter squared per second squared. Kilogram meter per second squared is a force. Kilogram meter squared per second squared is a joule. It's what? Huh? Oh, yeah, the meters per second squared. I got you. Okay. Now, let's start. Oh, do we know our mass? (1.0 kilogram). Okay. We're looking for velocity, so we know everything else. First thing I want to do is get rid of that 2. So let's multiply both sides of the equation by 2, get rid of the 1/2 there, and that gives you 1.0 kilogram times V final squared is equal to 19.6 twice times 9.8 kilogram meter squared per second squared. Okay? And now what we got to do is divide by 1.0 kilograms. Again, the 1.0 doesn't do much for us, but the units sure come in handy because that doesn't change the number, but you do lose the units. So now we got V final squared is equal to 19.6 meters squared per second squared. So how are we going to get V final out of that? Take a square root. If any of you got a calculator, do it. Can someone just look at that number and tell me it's between what 2 integers? 19.6 is between what 2 square root of that? Between 4 and 5, because 4 squared is 16, 5 squared is 25. This has got to be between it. So if someone's got a calculator, square root of 19.6. Say a little louder. 4.42 meters per second, because you don't only take the square root of the number, you take the square root of the units as well. Meters per second is a great number for a velocity. And let's see what we've got. I don't think we need the 2 there, so let's just call it 4.4 meters per second. Because you see, you've only got 2 digits here, 2 digits there, actually only 2 digits there. So nowhere do we have more than 2 digits. We kept it here because we're going to use those digits, but at the end, just round it. So let's see how the book, oh, look at that. They got it wrong, though. Did you notice? Or at least in my book, it's wrong. You see the solution 3.9? What's wrong with that picture? They got meters times second, which is absolutely wrong. It's meter per second. So you change that dot there to a slash. Meters per second. Did your book have it right? Sometimes the new ones do. They have it wrong too. On around page 73. Huh? Oh, 75. Okay, is it 4.4? Do they put? Okay, what the unit after it? Okay, it's not M times S, it's M divided by S. So they got it wrong even in the new printing. Sorry about that. Okay, meters per second. Any questions on that? Okay, let's go to 310. Now, I hope you noticed on that last test, there were what, about 3 or 4 you actually have to do calculations on. That's why I like to go over these in the book so you'll be ready for them. Right? Okay, let's do 310. What is the kinetic energy? So we're looking for KE. This is the unknown. Kinetic energy of a 1 kilogram book. What's that? Mass. Okay. Just before it hits the floor after. Oh boy, what a dumb question. I wish I had read this before I started. What is the kinetic energy of a 1.0 kilogram book just before it hits the floor after? It's the same as the problem 3.9, but I've already erased 3.9. But you know what they do? We use the kinetic energy to get it, and we found that kinetic energy to be 9.8 meters, 9.8 joules, remember? So what are they doing? They're taking this backwards and taking their rounded answer. Remember, it was 4.42, but we rounded to 4.4, backing up from it, and they get 9.7. Look, we did the problem using that. It's 9.8. I think they're ridiculous to use 9.7. just because they did the problem backwards and then lost a unit of digit precision. Sort of dumb. We actually already calculated that, and it was 9.8. Okay. Okay. All right. Energy conservation. Okay. And actually, before we get here, I really regret that they do not have figure 318 on the slide set. If you got your book, and if it uses the same number, this is a great figure to have. This is showing some of those energy conversions. It's 3.817 yours? Okay. Whatever it is, there it is. You have nuclear energy of the sun, that, or laser-induced fusion, gamma radiation, all this coming into, fortunately our atmosphere is blocking most of that gamma radiation. That's what's so bad about a nuclear bomb, and nuclear explosions, and nuclear reactions. You don't have the atmosphere to shield you from all that radiation. And you still got that radiation. So what they have to do in nuclear power plants is build big, thick walls to contain that. Sometimes line them with lead. Have you ever been to the dentist office and they've done x-rays on your teeth? Do they stay in there while they're doing those? No, they leave the room, don't they? Because they're exposed to that all day long. They don't want to be exposed to it. They get in those little rooms they're in. Notice the glass is sort of dark there. Leaded glass. And I guarantee you that wall contains lead in it. They're trying to protect themselves from that thing. Now, you're just getting hit by a little bit. They turn it off. That's all. No big issue. You know, those guys, people are in the room all day long. And they have those, they have those aprons on. Those aprons are heavy because they're lead-lined aprons. And that's just little old x-rays. That's not gamma rays. In a nuclear explosion, leakage and stuff like that, all kinds of mean and nasties are getting out there and nothing is protecting from it. I think I told you of the older Japanese men, what they did at Fukushima. Did I tell you that? No. Oh, I didn't? Oh. You know what I mean by Fukushima. Does that ring a bell? Yeah, the nuclear plant in Japan, that when they had the earthquake somewhere underwater, it had a huge tidal wave and it smashed into the nuclear power plant, and probably the earthquake shook it too. And they had a major meltdown. Okay? Lots of dangerous radioactivity was released. Okay? But Japan built things very, very safely, but they couldn't keep this from happening. But you didn't have something like Chernobyl, which exploded and damaged that, for miles and miles around. But it still was pretty major. They needed people to go in there and do as much cleanup as possible. I have utmost respect. The older men in those communities said, look, you guys working at the plant, these were retired men, they didn't have to do it. They said, look, you're the future of our community. We're the past. Let us go in and clean them up. We know it's going to kill us early, but we don't have that much longer to live anyway. Don't you risk your lives. Because they were going to die, It wasn't going to be immediate, and it could be long, slow, and painful, but it was going to do pretty bad damage. And they volunteered to go in and do the cleanup. My hat's off to them. I mean, incredible. Okay. So anyway, off into that. Sorry. So you have the nuclear power from the sun, which is giving forth all kinds of energy. Gamma radiations, X-radiation, light radiation, infrared, all sorts of radiation is coming out. That radiant energy either goes by photosynthesis to form store chemical energy, or you oxidize that and it goes back to be light, or like a fire or something like that. You can have that radiant energy collecting that as a heat engine and making mechanical energy, or mechanical energy changing the friction, which could produce light. Doesn't usually, but it could. You could have that radiant energy hitting the solar cell, producing electrical energy, or the electrical energy going through a light bulb, producing radiant energy. Back and forth, all these conversions can happen. Or let's go over to chemical energy. We've already talked about oxidizing to become radiant energy, light again. Or it could go through heat engine. You're burning that fuel, like in your car, and forming mechanical energy, energy of motion, or position. Or mechanical energy, friction, burning, going back to chemical energy. Okay? Or the chemical energy in a battery, a fuel cell, changing to electrical energy, or electrical energy, electrolysis, going back to chemical energy, charging the storage battery. Or, there's lots of things that could be going on there. The mechanical energy could be used to generate electricity, or electrical energy could be used to run an electric motor, which makes mechanical energy. Back and forth, either way, these energy forms are converted one way or another. Pretty great illustration there. Well worth your look. So now I think we're ready for energy conservation. Energy is never created nor destroyed. Eating your beans and potatoes doesn't give you energy. You're just converting it from stored potential, chemical energy there to energy of motion once you eat it. Okay? Energy is not created nor destroyed. Okay? Energy can be converted from one form to another, like that last illustration showed, but the total energy remains constant. Okay? An example of that is free fall, like your pendulum. You drop something at rest, no kinetic energy, but you have potential energy because it's above the floor. When you drop it, the potential energy decreases as you go down, but kinetic energy increases as you go down. Just a very simple example of that. Energy transfer mechanisms, work and or heat. You work, you add energy to a system. The energy works, it does energy on the system. You heat it up, it can do more work, or it releases its heat and performs work. Okay? Those are the mechanisms by which a lot of these transformations happen. Either work and or heat. And we'll talk about those even more later. Okay. What is it, 3 o'clock? We're getting close to that now. Okay. Now, because energy is never created nor destroyed, if you have only kinetic energy, say in free fall or something like that, you're only counting on mechanical energy. You're losing potential energy as it falls, but you're gaining kinetic energy as it falls. That loss here has to be the gain there. There's no place else for it to go. Almost. In reality, yeah, it's hitting air molecules and speeding them up and giving them a little bit of heat. But that's negligible. Okay? So, if the potential energy loss, that was the mgh is what you had at the top, and all that's going to be lost by the bottom, and your energy gain, you had 0 kinetic at the top, but maximum at the bottom, V final at the bottom. So this is, the loss here is equal to the gain here, that's 1/2 mv final squared. If you solve this for V final, which I wish I had put this on this side and that one on that side, but it's okay. Exactly what we did before. Multiply both sides by 2, so that gives you a 2 over here. You lose the 2 there. You divide out the m's all together. It didn't matter what the mass was. So you have 2gh. Take the square root of that, and you got v. And that's exactly what we sort of wound up doing in that last problem. If you remember early on, we multiplied by 1 kilogram. Later, we divided by 1 kilogram. So you lost the m's, and that's really what you were doing. 1/2. The square root of 2gh. Okay. Now, if you recall, back in the projectile motion lab, I think you saw that same formula, wasn't it? Square root of 2gh. I believe that same one we used when we were doing velocity. I believe we did, or something pretty close to it anyway. All right, here's another illustration of that. Let's say you're starting 10 meters high. How far is 10 meters, by the way? About what? Oh, yeah, you may be right. I'm about 2 meters tall. My waist is about 1 meter, and then the top part of my torso is about 1 meter. So the ceiling is pretty close to another meter, wouldn't you say? So this is a 3 meter room, approximately. Okay, a little over 9 feet, probably pretty close to 10 feet. Okay, so this would be about a 3 meter room. So 3-story buildings with a little bit of space in between each story where you have all your mechanical stuff, that's going to be pretty close to a 10 meter building. So get on top of the building here, the part that has 3 floors, that would be about 10 meters. It's pretty far up there, by the way. Okay? That's where you're going to release the mass. I don't think they tell you how much mass, but guess what? It divides out anyway. You see mass anywhere here? Not really. Okay? But they do show it here, mgh. So I think what we're going to use is 1 kilogram. Why not use just 1 kilogram? Okay? So, yeah, because look, 10 meters, that's your h. G would be 9.8. Your mass would have to be 1. That would be 98 joules. Velocity is 0 because you're releasing it, not throwing it, but releasing it. So velocity is 0, and this velocity is 0. So your kinetic energy at the top is 0. Okay? All of your mechanical energy is in that gravitational potential energy, mgh. Halfway down, 5 meters, you're down half of your h. It was 10 here, it's 5 here. That's going to be 49 joules there. Does that mean you have half the speed you will at the bottom? No, because the faster you go, your kinetic energy is increased by, you double your speed, you multiply that by four times. So this is not going to be twice that. Okay, but it does work out. 1/2 mv squared. If half of this is potential, half of it is kinetic. So 49, you move backwards from here to figure out the velocity there. At the bottom, if your reference height was the ground, then at the bottom, you're at 0 as it hits. All of your kinetic energy down here was your potential energy here. You get this, all of it's 98 joules that you had up here. All the mechanical energy is not kinetic. And you take your square root, and you can get that's 14 meters per second. Okay. You can work that out slowly if you want to, but let's move on. All right. Okay, that was energy conservation. Now we're talking about energy transfer, which they're calling flow of energy. Okay, different slide title. But energy transfer. It's almost like we've said this over and over and over again, but it's still true, and that's why they're emphasizing. Energy is never created nor destroyed. It can be converted from one form to another, but the total energy remains constant. Here's that same illustration just with pictures now. The nuclear energy of the sun is going on constantly. Some of that energy makes its way through our atmosphere as radiant energy. And we have James here. Okay. And those hit the little green leaves out here. The little green leaves go into making more cellulose, storing this radiant energy as chemical energy. Later they'll eat the apples and the pears and the other things coming from the green plants and store that as chemical energy in the body. They can burn that chemical energy in the body and ride their bikes or whatever they want to do, sweat and build and expend heat, and that heat radiant energy goes back into our atmosphere. Now, can it be used again? Well, in a sense, it's used to melt snow and stuff like that. but a lot of times that's just sort of wasted energy without really a lot of obvious use for it again. That's why it's converted, but may not be converted into anything usable. All right. So let's now look at energy sources today. This is 3.4, which I think, nope, it's not the last section, but it's the beginning of the end of the chapter. Energy sources today. Now this is a little bit of an old slide here. It may actually be a little different from what's in your book. It is slightly different from what's in your book. I'll try to update this as we go. The book is a little newer than that. Some of you with newer books than mine may even be more than this. Believe it or not, we're actually using less petroleum today than we were when this was done. 37% in the book now, and this is old data, 40% probably 5 years before that, maybe a little more before that. Why do you reckon we're using less? We're driving less? And we're driving a whole lot more. We've got other forms of energy we're using more, okay? Some of our cars are now electric. Some of them are more hybrid cars out there than we had before. And hopefully all of the cars are more energy efficient than what we had before. So petroleum is slightly on its way down, but really it's the percentage going down rather than the total amount. But the other thing is there's less petroleum available now than there were 10 or 15 years ago. I mean, there's still plenty of it out there, but it's not as much as it was then because we've used it since then and we haven't made any more. Not that much more anyway. So next after petroleum at 40% here, 37% here, coal. Now this is surprising to me. That stayed 21% in both. That's not happening anymore. I bet you today, if you were to measure that, that's gone down more than the 3% here. And why do you reckon? Natural gas has gone up. 25% in the new edition, 23% here. I would say since this book was printed, it's gone up even more. Why? Say again?
I was at 27.
27. Very good. See, it keeps going up. What did it say about coal?
18.
18. See, I told you that was dropping. How about petroleum?
36%.
36. Dropped even more from this. It was 37 here, 36. Natural gas going up. Why? What are we doing now more than we used to? Haven't y'all heard of fracking? They have come up with new techniques and ways of getting natural gas out of a variety of things. In fact, the U.S. is really getting close to being energy independent. Yeah, we still get a lot of energy from Saudi Arabia and Venezuela and Nigeria and other countries like that, but we are more and more providing natural gas. We have plenty of coal. We export coal and we export probably some natural gas. Okay. Unfortunately, the coal that we export, we send to South America and other third world countries where they don't have as stringent pollution controls because our coal is kind of dirty, you know, especially that in Alabama. It's a pretty high acidic coal. So we export that because it's too dirty to burn here. We let them burn it there. Guess what? We still are in the same atmosphere, folks. You know, it's just there. So natural gas has gone up. Nuclear, how did that compare? It was 9%, 8% here, 9% here. What is it in the new book? Nuclear. 8. Still? Oh, it dropped back to 8. Okay. Again, that's probably because it's really a couple of factors here. Number one, the older nuclear plants, they are beginning to cut back. And as far as I know, in the U.S., there's only been maybe 1 or 2 new nuclear plants in the last, I'd say probably close to 30 years. Anyone know why? What's that? There may be a little bit, but I don't think really the EPA does too much. I mean, I'm sure they do something with nuclear. But what happened, I can't say exactly how many years ago, but it was, I'm guessing, close to 30. Anyone hear of 3 Mile Island? What was that?
You said 30 years ago?
It may not have been 30. Huh? Okay. I thought maybe you studied history or something. No. What's that? They had a pretty major nuclear problem there. They had a minor meltdown. It didn't pollute the way Chernobyl did. Chernobyl was a disaster, a total disaster. That was in what was in the Soviet Union. Is now in what we call Ukraine. Have I told you any of that story? See, I teach so many classes I can't remember. About a year and a half ago, I guess it was, maybe 2 years, time slips by so fast. Had a kid who sat right back there in the corner in Math 100, and then a later term he was in my Math 112 class. He still sat in the same place. He was born in Ukraine. I don't know if it was Soviet Union then or Ukraine, but he was born there. He was born with only one arm. This arm had maybe a finger or something. I mean, it was really bizarre. Nothing was there. He had cleft palate. He had some learning disability. Really looked barely like he was going to maybe even survive. His parents gave him up as soon as they saw him. We don't want him. So he was sent to an orphanage. And the orphanages in Ukraine were not probably the best places in the world, okay? And fortunately, a couple from the U.S., from Birmingham, Alabama, adopted him as a very young baby, brought him over here, given him a really good life, and he was going to Jeff State. He just had trouble with math over there, so he came here and took it. And he did okay. And I imagine now he's gotten his degree in physical therapy technician. He wanted to work with other kids who had mechanical problems. Great guy. He was born in Ukraine. He couldn't have been more than 20 years old when he was in my class. And Chernobyl happened long enough ago. It was like what happened to his parents were transmitted to him. They didn't lose any limbs, but it damaged their DNA. So when they combined together to form a child, it was a defective child. Because of that really major nuclear disaster that happened there. There were churches here in Birmingham, I'm sure throughout the U.S., that made it one of their goals to send for kids over there who were exposed to that most of their lives, bring them over for a summer just so they could develop in an environment away from the nuclear contamination that they had in their own home country. So a few fortunate ones like him got adopted here. The others were sent back, but at least they had one summer to develop somewhat normally. It was a disaster.
How many miles did that span out?
I don't know. It was pretty far. I'm guessing,
Hundreds of miles?
possibly. I'm guessing the really severe was probably more like 20s, 30, 50 or something like that. But probably there was some effect as much as 100 miles away and maybe further. I don't know. It would be a good paper topic if you're interested in it. Chernobyl, it's incredible. Someone actually did write a paper on it either last term or the term before about this mass of melted material that is that they call it the fist or something like that. That is no one's been able to get close. They've sent robots in with cameras and taking pictures of it, but it's deadly stuff. I mean, they still
It's
do
like
it
that now. It'll be like that
for thousands of years. Okay, unbelievable. Okay, well, our 3 Mile Island was a mistake, an accident, and maybe somewhat of a meltdown, but it was all contained. Our safety that we build into it, and that's the thing, we build so much safety, backup after backup after backup. The Soviets, they just built the plants as fast and furious as they could. They didn't have that in place. Our 3 Mile Island could just have easily been a Chernobyl. I don't know what caused either one of them, but they did. After 3 Mile Island, I don't think there was another, even though it was not a major thing, I don't think there was another nuclear power plant approved in the U.S. for at least 20 or 30 years. Okay. The most recent was in Plant Vogel over in Georgia. It's part of, it's right across the Savannah River from the county where I grew up. And they have they've added another, they've been operating for a while on 1 or 2 reactors. They just recently in the process of adding another one. And the electric power lines that are going to feed Atlanta and other places cut across, not our farm, but you can see them from our farm. So, yeah, that's why nuclear may have gone up a little bit, it's going back down. We just aren't doing that much new. And since Fukushima in Japan isn't doing any more nuclear, isn't doing any new nuclear. In fact, probably cutting back some of their old. I don't think France or these other countries that were counting on nuclear, they've also cut back. This is mostly U.S. side. Okay. After this is biomass. They combine biomass, hydroelectric, and other geothermal, solar, and stuff. They combine it all to renewable in mine. In mine, that's 8%. This is 3, 3.5, and a half, so that would be 4. It was 7% here. This is growing. But it's so small, it's going to take a lot of growth to replace these, or even that. If you notice from here, almost between a third and a half is petroleum. Around a fifth is coal. More than a fifth, close to a fourth is natural gas. Nuclear is less than a tenth, and this other little bit is tiny. Okay, even though that may be growing, it's still got so far to go. Okay, so primarily energy sources today are things that came out of living plants: wood, coal, petroleum. Wood to coal to petroleum. With increasing industrialization, in the past we were using mostly wood, then we went to charcoal, then to coal, and now to petroleum, and now to natural gas. Increasing industrialization. 89% of the energy in use today is traced to photosynthesis. That came from photosynthesis, that came from photosynthesis, that came from photosynthesis. Add these up, 40, 60, 84%, plus 5% from updates to this, okay, came from photosynthesis. Not the little bit of wood, that was recent photosynthesis. The rest of this is photosynthesis that happened literally thousands of years ago. And we're using that as fast as we can get to it, basically. We can't continue that forever. At some point, we will run out. We've got to be expanding some of these others. Uses, about a third of energy is used for heating. 2/3 is burned in engines or generators. Generators to make electricity, engines to produce motion or whatever directly. Okay? Those are approximate figures. So let's look at each one of those. Petroleum is basically an oil from oil-bearing rock. Now, I don't know. I've always pictured petroleum as being, you stick the pipe in the ground, you hit a thing, here comes the oil out the top. That's what the movies always showed, right? Most of that's all long been used up. They may find a little bit somewhere around, but most of it is from oil-bearing rock, which means they have to extract it from the rock somehow. And they do various things to do that, like pumping very hot water down there and getting it to come out, or pumping other chemicals down there. Some of it may still be under pressure and come to the surface, and they don't have much to do to get it except contain it. Now, where did it come from? Organic. Now, what does organic mean? From living things. Okay, organic sediments, which are the residues from living things that have been transformed over time by three things. Biologically, by bacteria, pressure, that's the physical process, temperature, that's the physical process. This is an endothermic reaction, okay? Bacteria are involved, pressures involved, high temperatures are involved. That's what converted those organic sediments into petroleum. Now, natural gas comes almost the same way. Very similar, except usually at higher temperatures and maybe higher pressures. And maybe a few more bacterial action, okay? But natural gas and petroleum, they go sort of hand in glove. But sometimes with natural gas, like the fracking now, is coming from rock itself. They're getting it out of rock. Of course, they're having to do all sorts of stuff to get it out of there, like pumping all kinds of chemicals down into the ground to get the natural gas to come out, free it from the rock. That's the process that we've just started doing it like in the last decade or so, and people are a little worried because we don't know, since it's not been done for very long, we don't know what is happening, okay, what it may be causing. One thing that's very frightening, I believe it's Oklahoma, has had, I think, something like 50 to 100 times more earthquakes. Now, they're not major earthquakes, but they're earthquakes, shaking of the ground than what they had before they started fracking. And the thought is that what binds the earth together there is being sort of lubricated by all these things they're pumping into the ground, and so any pressures are releasing now, and they're having earthquakes. Now, so far they've not been major, so maybe it's not a big deal. Unless you happen to have a house or an area that has a lot of these, it may be hard to sell your house. I don't know. Okay. This is okay. So like we said before, natural gas and petroleum often found together, but they also can be found from other rocks. The supplies are limited because, like I said, the petroleum and natural gas were formed by photosynthetic processes that happened thousands of years ago, and we have been using them as fast as we can get them out of the ground. So we're not making them that fast anymore, so we're using them faster than they're being made. Supplies are limited. 25% are from offshore wells now. Does that ring a bell that might raise a few flags? Offshore wells? The what? The BP oil spill. Offshore well, I didn't know that the Gulf of Mexico went down as far as a mile deep. It obviously does, and maybe much deeper. And that well was way offshore and more than around a mile deep, which is just unbelievable. I can't even imagine it. And at a mile deep, the temperatures down there were close to 0 degrees. And how do you get things to operate well at that colder temperatures, that far away, remotely? That's why that thing gushed out oil for week after week after week into that beautiful Gulf of Mexico. Now, fortunately, the Gulf of Mexico, warm water, high temperatures and stuff, a lot of that oil has been dealt with, but there's probably more still down there because at those low temperatures it's very dense and coagulated, so it's sitting on the bottom. So who knows how long that kind of exposure, what that's going to do to marine life over the long run. We think the worst of it's over with, but we don't know. They say more than 50% imported. I bet you today less than 50% is imported. And probably, I don't know, that may have gone up some, but we're just using less. Okay. So there's petroleum. Coal, very similar. Accumulated plant materials, organic matter, just like thing, processed over time. We talked about how long, by pressure and by temperature. Now, they didn't mention the bacteria and other microorganisms. They're still involved. But your progression now is from the plant material to what they call peat. Peat bogs, you can still see traces of plant material, leaf stuff in that, to lignite, which is a hard rock and mineral type thing, to subbituminous coal to bituminous coal. Now that's the best kind, bituminous. There is another kind called anthracitic coal, which has a lot more sulfur in it, and that's mostly what we got around here. We do have probably some pretty good coal, but most of ours is too acid. So that's why we ship it to other countries where their governments don't control the air pollution as much as ours do. We import a lot of our coal from Wyoming and places like that where they have more of the lower sulfur bituminous coal. But all coal, no matter how good it is, contains impurities. Some of these are minerals, like silica type minerals and other minerals, and those don't burn away, so you have ash left over. Some of that ash may be, have some beneficial thing, sometimes some very non-beneficial effect, sometimes sort of neutral effect, but it still leads to ash. The sulfur is in all coal, and that leads to sulfur dioxide gas. Now, what's wrong with sulfur dioxide gas? You say it's good stuff?
Apparently it ain't good.
It's what?
Apparently it ain't good.
Okay. It's in the air, and in the air you also have water, plus sulfur dioxide. A chemical reaction, when those combine, what do you get? H2SO3, which is sulfurous acid, very close to being sulfuric acid, which is one of the strongest acids you got. In fact, where do y'all see sulfuric acid? Probably almost daily in your batteries. You want any of that on your clothes or skin? Definitely not. Otherwise, you won't have clothes or you'll have very hurting skin because it eats it up. It's a pretty strong acid, and that's why you don't want that much sulfur dioxide gas going into the atmosphere. That produces what they call acid rain, and acid rain can kill trees, and it has killed many trees and done a lot of damage to soils and to people. Okay, so no, it's not a good thing. Petroleum, natural gas, and coal are all what we call fossil fuels, meaning they are fuels from plant material that happened thousands of years ago, fossilized stuff, okay? And we're using them much faster than they were developed or formed. We can't do that forever, okay? We may not be close yet, but one day we will be close, and then what are we going to do? Now, here's a renewable resource, moving water, okay? How is that an energy form? Second? Yeah? Yes, when you do these hydroelectric dams, and look around Alabama, Lewis Smith Dam up in, is that Walker County, somewhere right up in there. Logan Martin Lake, I'm sure, is a hydroelectric dam. Lake Martin's a hydroelectric dam. I don't know, is Purdy a hydroelectric? Is that just used for drinking water? I don't know. It doesn't have, yeah. But we are so fortunate. We have enough of a drop off from the high parts of Alabama to the low parts that we have fantastic water resources. Okay, we sell a lot of our electricity to other parts of the country because we produce so well, but guess what? Well, we'll see that. This is renewable with rainfall. Okay. The hydrologic cycle, vast portion of the Earth's surface, 2/3 or more, covered with water, the oceans. The sun hits that water, evaporates the water. It goes up into the atmosphere. The very humid air gets blown over land masses, cools off, it comes down as rain. Renewable with rainfall. Natural process. The gravitational potential energy that it gains when the water is evaporated and goes up, that loses that when it comes down, hits the ground, goes downhill, picks up speed, the potential energy changes to kinetic energy. If we can catch that in our dams and convert that to electrical energy, your hydroelectric dams. And we produce a lot of that. However, hydroelectric plants generate only about 3% of the U.S. total energy consumption. Why? Because most of the easy to locate and place dams have already been in place. We started building them back probably 30s or 40s or even before that, probably. Been building them for years, but guess what? Not that much place. Okay. Do you think anyone would agree to dam up the Cahaba River anywhere else? It may already be dammed in some places, but no, it's used for recreation, it's used for lots of things, and it doesn't fall that much anymore. They've got the dams up in the high parts. That's where they're best. Down near the coastal plains, if you tried to build a dam there, you'd flood counties with water, And in fact, it's hard to find the place you go. Lewis Smith Dam, a lot of that area is Winston County, which is probably one of the poorer counties in the state. Back when they built it, they could afford to buy that land and sink it underwater, okay? You can't afford that anymore. Most of the growth potential is limited by decreasing availability of new sites. You just can't dam that many more rivers and get away with it. Too many people like their land, they don't want to sell it or get rid of it, okay? So moving water, very limited. Fantastic source of energy, converting to electricity, but we're down to 3%, and it's probably going to be dropping because other things are going to be increasing. Nuclear, we've already talked about some of its problems based on nuclear fission reactions that occur. No, that's not well. The nuclear power that we create is nuclear fission of uranium, plutonium, these huge atoms that break up easily or relatively easily and give off lots and lots of energy. Also give off lots of pollution, okay? The water is heated in the reactor, then used to produce steam, generating turbines to make electricity that way. Plant Vogel, I know in Alabama there's some, I just can't remember the names of them. The safety of nuclear power generation is controversial. We have probably some of the safest on the planet, but so did Japan. A natural disaster happened, they had a major problem, okay? So, how safe is safe enough? Hard to say, hard to say. And they're not even, that's just a little bit of it. Even of these very successful nuclear power plants, very safe nuclear power plants, never had any problems, people never get exposed to radiation. Guess what? When they finish using that uranium and plutonium, what you have left over, the wasted fuel, the residue from that, is highly radioactive material that is going to be around thousands of years. What do we do with it? Right now, I think there's a mountain in Utah. I believe its name is Green Mountain or White Mountain or something like that, that they are burying as much of this nuclear waste as they can. I think they're just about reaching the capacity of what those people are going to put up with. And they're putting it in the best sealed stainless steel containers they can build. Okay? But nobody knows how long, what the life of those containers are, and what's going to happen if and when they ever start leaking. And what's going to happen, where is that stuff going to go? It's inside a mountain, so it's surrounded by rock, but all rock have fissures, and that could get into groundwater. If it gets in the groundwater, how many people is it going to affect? It's going to be around thousands of years. What do we do with the waste? No one's answered that. They're not even talking about safety of nuclear power there. What do we do to the waste with the safest nuclear power plant? And guess what? Not just nuclear power plants. All the nuclear ships, submarines that we have in the U.S. Navy and things like this, they're all producing this waste product. I don't know the answer. Okay. All I know are some pretty scary questions. So, energy sources tomorrow. Okay. Before we go off of this, and why in the world do they have this in here except it just has to do with energy? Myths, mistakes, and misunderstanding. Here's what they say. It is a myth that leaving your computer on all the time uses less energy and makes it last longer. Have y'all ever heard that before? Okay, you're probably too young to have heard it. But in the old days, that was what they thought, you're going to tear it up by turning it off and on all the time. I've heard the same thing said about fluorescent lights. Better to leave them on than turn them on and off. Well, sure, you got to charge that capacitor in there that keeps it, the ballast that's in there. That's where most of the energy goes. So turning it off and on too frequently, you might actually really do. Yeah, and it may run up the voltage more. But guess what? They've made those so much better than they used to be. That's not really an issue anymore. And certainly computers are the same way. It's going, the more heat you produce, the more likely you are you're going to cause some failure. Leaving it on all the time is producing more heat. And you know what? The major problem, in my mind anyway, and I'm not a computer person, but most of the computer failures I know about have come from fans going bad. If the fan quits running, they overheat and it kills the computer or it does a lot of damage to it. Guess what? Those fans can't work forever, okay? The longer you run them, the shorter line they got left to run, okay? So that's a mistake. Myth. Science and Society, on my page 76, somewhere along that, grow your own fuel. Now that's fuel, folks. Okay, never mind. Okay, grow your own fuel. Guess what? There are new ways they're making diesel oil. Does anyone know some of these? Cooking oil, exactly. This used cooking oil that people throw out, used to throw into the garbage. If you've ever been in an alley near a restaurant, you know how much that can stink, okay, because they throw out the old oil. Now they're beginning to collect that. And don't they also collect burnt motor oil now and reprocess it? So all this now, the cooking oil is mostly vegetable oil. Safflower oil, corn oil, peanut oil, soybean oil, various oils. That's grown, and after you use it for the other things, then the residue, convert it to biodiesel. Okay, that is a very good. And then the burnt motor oil, that was originally the thing. But rather than throwing it out, redo it. And nowadays, how are synthetic oils now? Are they up to par with naturally produced oils? Better even? What's that? A little better. They're still a little more expensive though, aren't they? A whole lot more. But they'll last longer. Okay. How do they make those? Do you know? Okay. Be a good paper topic if someone's interested in it. I'd love to know that. But so there are things out there. Growing your own fuel, yeah, good possibility there. That's fuel now, folks. Don't go anywhere else with that. Okay. Now, there's a people behind the science. James Prescott Joule. They named the unit after him. He was a very fascinating character for many, many reasons. One of which, in the old days in England and most of the European countries, this was mostly before America was either on the scene or really a part of the scene yet. Remember, they had the feudal system. You had the rich landowners, they were called the landed aristocracy, and they were the people who got the education and did the things. And then you had all the poor people who were the serfs that worked on the landed aristocracy. Well, when the Industrial Revolution was coming along, then you started having a middle class, tradesmen and people who worked in industry and things like this. They weren't considered as high as the aristocracy. They still had the land, the power, the people, money, and that kind of stuff. But all that was beginning to fall apart, okay, or not be viable anymore. Well, James Prescott Jewell came along, and his father, if I'm not mistaken, was a brewer. He brewed, I don't know if it was beer or some sort of alcoholic beverage as part of that new working class, and they were making money hand over fist, and suddenly the aristocracy weren't the richest people around anymore, though they thought they were, and they acted like they were. Well, he was the son of a brewer, so he had a chance at education, and this is a strange way to say it, fortunately he was a sickly child. Some people think he may have been hemophilia. You know what that is? The free bleeders, if they get a cut, they can't stop the bleeding. They don't have the platelets or something in the blood, and they can bleed to death, so they can't really do a lot of physical stuff like working in a plant where they could get cut. So he was a very bright child, but very sickly child, and because of that, he learned things extraordinarily well, but he still may have turned out nothing if it hadn't been for one of those rich aristocrats, Lord Kelvin, William Thompson, who looked at some of his work and said, this guy is really good, and he brought him into the Royal Society, and he got published, and he did really so much to advance what we understand about heat today. That's why they named the unit for energy after him. Good paper topic. This can't be your source, though. This may give you the idea you need to find your source somewhere else. There's concepts applied, city power, that's well worth a read. Some of the numbers are astronomical, and I think for a reason. Okay. And then mistakes and misunderstanding. Recycle or reuse, and that's just talking about our misuse of some of those words. The more we can recycle and reuse, the better off we are. And I swear, every time I go to the grocery store and then realize I forgot to bring any bags that can be used again, and I take home more of those plastic ones, I go, yuck, here I am contributing to the problem, not being a solution to the problem. But there's lots of things we can do every day to recycle or reuse, including recycle. So now we're ready for 3.5, which now I think is the last section in the chapter. And, oh man, is it 3:45 already? Yeah. Now, here's the little dilemma, and it's not really much of a dilemma. We're well past the place that we can do the lab today. It's not going to take us 2 hours. Okay, but if we don't finish the chapter today, that means I don't want to test you on it on Thursday. That'll mean it'll be next Tuesday before we test on the chapter. We'll already be into chapter 4 by then. Is that going to be a bother to you, or would you rather have the test Thursday or next Tuesday? That's what it comes down to. I can get through these slides probably in less than 5 minutes. Huh? Oh, yeah, the test is the same. It's just whether we're into chapter 4 when you're taking the test, or the chapter 3 is closer to your mind. It's up to you. Would you rather have the test Tuesday or Thursday? If you want it, huh? You want, not day after tomorrow, next Tuesday. Huh? No, I'm just asking. If y'all really rather have it, not have it Thursday and have it next Tuesday, that'll be fine. So we'll stop there and pick up on energy sources tomorrow. Okay, that's where the slide is now. And we'll proceed to lab. Now, lab will be down in 259 again, not in 253 or 252. Down in 259, the one we were at last time, I believe, right?
Yeah.
down there. Don't believe there's a class there, but why don't you take maybe a 5-minute break or something like that? Let's see.